Catlin back with you for the last lesson. It's the last 2 pages. We're going to squeeze this into one video. Priya, she's got a pregnant cat. It's going to have 5 kittens, a litter of 5. Each kitten has 30% chance of being a beautiful chocolate brown coloring. Priya wants to know, what is the probability that at least 2 of these kittens are going to be chocolate brown? What a strange wonder. And to simulate this, Priya wants to put 3 white cubes and 7 green cubes into a bag. That's a total of 10, 3 of them being white. She's simulating 30%, 3 out of 10. For each trial, Priya is going to pull out and return the cube 5 times. So pull out, put it back, pull out, record, put it back, pull out, so on and so forth, over and over and over again. She's going to do that 5 times for each trial. And then she's going to do the trial 12 times to simulate the cat having birth 12 times and recording all the possible ways this could play out. All right. So the first time that she did it, she pulled a green cube out every time and didn't get any chocolate brown kittens. Shameful. How dare her even think about doing that? But it happened. Okay. It happened. We just got to get over it. But she did this 12 times for a total of 60 cube pulls. So she's really curious about this. And we're going to answer these questions about it. How many successful trials were there? Well, the definition of a successful trial to her was having at least 2 kittens that are chocolate brown. And chocolate brown down here would be W's because those are the white cubes. So none there, not on that one. Only 1 on that one. 3 there, that would be successful. 1 there, nope. 1 there, nope. 2, that's at least 2. 1 there, no. 2, yes. 2, thank you very much. 1 and 2, okay. Got to scroll down a little bit for that 12th one. Oh, wasn't successful because only 1 W. So 1, 2, 3, 4, 5. 5 successful ones. Describe how we determined if there were 2 or more W's in trial. Part B. Based on the simulation, estimate the probability that exactly 2 kittens will be chocolate brown. Exactly 2. None. 1, 3, 1, 1, 2. Bingo. 1, 2. That'll work. 2. You know that's 3. Can't count. Sorry. 1, 2. Booey. 3 out of how many trials did she do? 12. That would be a 1/4, or I would estimate about 25% chance that you're going to have exactly 2 chocolate brown kittens. Part C, based on this simulation, estimate the probability that at least 2 kittens will be chocolate brown. Okay, so that's kind of what we looked at the very beginning. Exactly 2 versus at least 2 will be chocolate brown. All right, so at least 2 goes back to what we did at the very beginning with the red. 1, 2, 3, 4, 5. That would be 5 out of 12. We're estimating about 5 out of 12 will be chocolate brown. Write and answer another question Priya could answer using this simulation. Okay. Let's write our own question. What's the probability that none are chocolate brown? What's that probability, Kemosabe? Well, let's look at the tape. Let's go to the trials here. So over here we got 12 trials, 12 pregnant kitten patches of birth happening, right? 12 of them. And how many of them don't have any chocolate brown? 1. No, that's got 1. That's got 1. They all got 1 except the top one. So I'm going to say the probability that none are chocolate brown according to these are 1 out of 12. E, last one. Let's go. Let's go. Let's go. E. How could Priya increase the accuracy of this simulation? Because I don't know how much I believe these results because she only did it 12 times. So I think to make it more accurate, she could increase the number of trials. That always tends to earn more accuracy when you do it more times. A team has a 75% chance to win each of the 3 games they will play this week. Claire simulates this week of games by putting 4 pieces of paper in a bag, 3 of which are labeled win and 1 that is labeled loss or lose. She draws the paper, writes down the result, and then replaces the paper and repeats the process 2 more times. This is a fantastic simulation for 75% chance because 3 out of 4 wins is 75%. For the first time, she gets the result win, win, lose. What can Claire do to estimate the probability that the team will win at least 2 games? Well, she can't base it off of that one trial. I mean, she can't say that it's a 100% chance because I got win, win, lose on this first one. What Claire needs to do is Claire should do more trials. Okay. After she's done more trials, say, I don't know, 10, 15, 20, 30 more, right? She does more and then set up a probability fraction based on the results. So, like if she does 20 more trials, how many of those 20s did we win at least two? Set up a probability. How many out of the 20 did we win more than at least two? And then that would be a good estimate. But you need more trials. You can't do it with just one. That wouldn't make any sense. All right, let's move on to the last page. Oh, here we go. Number 3. We have to list the sample space for selecting a random word from the or letter at random from the word pineapple. Okay, sample space is all the possible outcomes. So we could get a P, we could get an I, we could get an N, we could get an E, we could get an A. P, we've already said that. That's 2 more times, but yeah. L, we haven't got that one yet. There's another E, but this is the list of letters you could get. This is all the outcomes that could possibly happen. That's our sample space. A letter is randomly selected from the word pineapple. So we cut them all up, put them in a bag, and we randomly pull one out. What's more likely to happen? Selecting an E or selecting a P? Explain your reasoning. All right, let's do this. Probability that I get an E. Well, first of all, our denominator is the total possible outcomes, which is a 1, a 2, a 3, a 4, a 5, a 6, a 7, 8, 9. There's 9 letters in there. Even though the sample space has 7, some of them are multiple. So we got to count those as part of the total outcomes. So 9 of the ways to get an E, there are 1, 2. So 2 ninths to get an E. Let's look at the probability that we pull out a P from this sucker. Okay. Still out of 9, but there's 1, 2, 3 P's. So technically that's a third of a chance. And clearly 2 out of 9 is smaller than 3 out of 9. So less than. What is more likely? Pulling out the P is more likely. Pulling out the P from the bag of letters. And you know what? If I reached in that bag and I pulled out an L, I'd be like, sheesh, I don't believe it. Disbelief on my part. Because you know what? I looked up what your little sheesh means, and it's not bad at all. It's a perfectly good word. It's on TikTok. This is me being lame looking it up, but I did it. And it simply means disbelief. I can't believe it. Exasperation. Also, shock, surprise. So sheesh. Nothing wrong with it. It's not a curse word. I was worried at first that I was saying something bad, but it is a typical word. And it just means exasperation, shock, surprise. Can't believe it happened. Sheesh. There you go. So I feel better about using it now and not so much of, I do feel old for looking it up and having to look it up. But you know what? Life goes on. Look at number 4. On a graph of side length of a square versus its perimeter, a few points are plotted. Add at least 2 more ordered pairs to the graph. All right, so we got to be thinking here about table action. All right, we got table, we got our perimeter on one side of the square, and we've got our side length on the other side of the square. When the perimeter is 20, the length was 5. When the perimeter was 9, the length was 2.25. So we're looking at this. We're thinking about a square. Let's make up one. Let's say the perimeter was 4, or the side lengths were 4. What would its perimeter be? 4, 8, 12, 16. So when it's 4, it's 16. What are we noticing about the relationship between these? Well, let's put that one on there. 16 perimeter, 4. That would go there. Let's do another simple square. Let's do a 1 by 1 by 1 by 1. 1 plus 1 plus 1 plus 1 is 4. So that would give us 1 and 4 as our perimeter. So let's plot that. 4 perimeter, 1 as a side length. What are we noticing about all of these things? Well, I'm starting to see that we got a constant of proportionality timesing by 4 to come back this way, right? So we can multiply the side length times 4, but technically our constant of proportionality is coming back the other way because x is over here. So we're timesing by a quarter to shrink it back to the length size. But we added at least 2 more on there. So check to part A. We put one here and we put one here, and they work for a square. Is there a proportional relationship? And I'm going to check it right now. Does it straight line through the origin? Yeah, buddy. You better believe it. It's got yes written all over that one for a couple of reasons. Straight line through origin, right? That's one reason. And we could also say that it has a constant of 1/4, right? So there's like two reasons that you know that that is a proportional relationship between perimeter and length of a square. It's always 4 sides in a square, and they're all the same size. So you can just multiply the side length times 4, and it will always go to the perimeter, and you can always divide the perimeter by 4, and it will be the length. I'm obviously tired and saying weird things. I hope you guys have a great rest of the week. Good luck on your quiz this week, and that's it for your homework.